Hi, my name is Noor and I work with Dr. Kochunov at the University of Maryland. Today I'm here to show you how to use the GPU F5 command to perform a Voxelwise Heritability Analysis. The GPU command is an optimization of the F5 command for performing heritability in 3D imaging datasets. The command produces 3D voxel-wise maps of the additive genetic control over the traits encoded by voxel values. Examples of these traits include voxel-wise maps of fractional anisotropy and other diffusion parameters, or gray matter density maps from voxel-based morphology studies. The command works with the following assumptions. 1. That all voxel-wise data is stored in a single 4D Nifty file. 2. That the voxel-wise data for every subject has been spatially normalized to a common space. In other words, the data for all subjects in the same spatial orientations. Third, there is a binary mask file that defines the space of useful data. All data that is residing outside of the mask file will be ignored. 4. There is a set of covariates that is present for all subjects, such as age and sex. We provide a test directory that contains voxel-wise DTI data from Human Connectome project and the pedigree files, so you can run the analyses yourself. The link is provided at the bottom of the video. The process will be broken down into 3 parts. First, we will have to create CSV files from the Nifty files we received through the Nifty to CSV command. The reason for this is the memory requirements for loading large Nifty files. Nifty format allocates memory for the entire 4D volume, including the empty space outside of the mask. This wastes the precious resource and makes processing large datasets difficult. Instead, we will convert data into standard CSV form from where data for each voxel will be stored along the subject direction, therefore minimizing the data requirements. We are working on the imaging genetics format that will make this conversion easier, but it is not ready yet. Second, we have to normalize the values so that they take into account all the covariates we have included. Finally, we will use the updated GPU F5 command and then merge files to create a coherent map. To begin, we will navigate to the directory with our Nifty files, mask, header files, and the phenotype and pedigree files. First step is to make the pseudo-phenotype file that references the imaging data. The pseudo-phenotype file should have all the subject IDs and covariates that will be used in the heritability analyses. The phenotype should be referenced in this format, myimagingdata.nii.gz, and then, after a colon, the volume number, such as this example here. Examples of the phenotype file can be found in the directory available at the bottom of the video. Once you create such a phenotype file, you can use the Nifty to CSV command. You will also need your pedigree files for future commands, and they should already be set up. If not, please refer back to the pedigree tutorial. Now we will input the Nifty to CSV command. After opening our SOLAR package. Now that we're in the directory, I'm going to go ahead and input the Nifty to CSV command. First, you put in the command itself, and then you put in the mask volume, followed by the trait name column that you are looking at in your covariates file, followed by your covariates file itself. And then you're going to put in your output, which is, in my case, I'm going to have my phenotype file come out as KA voxelwise. We recommend a max number of columns to be 60,000. Now we wish to perform our heritability measurement on the CSV files. Before we run the GPU F5 command, to do so, we want to run sporadic normalize. This command will rewrite the trait measurements so that they are corrected for the effects of the covariates. In our analyses, we are including age and sex. Before running the command, however, create a header file that has all of the traits you wish to run your heritability analysis on. To do this, open Solar and then load your phenotype file, which is what you generated using nifty.csv. Select your covariates and then input the following command. So we are going to put in the commands sporadic, normalize, header, and what we want outputted. To run the GPU F5, I've opened my Solar I'm going to now load my phenotype files. I'm not going to load a pedigree file because in my folder I already have my pedigree files set up, so to just be able to read the files from there. And I'm not going to select any covariates because we've accounted for it in our sporadic normalize command, so the normalize.csv that we're using as our phenotype has already taken our covariates into account. Now we're going to use the header file we made earlier, and we're going to type in our command. Mask file, and then what we want it to output as. Now we get to decide what devices we want to use, whether we want to use all of our GPUs or only a couple. This can help distribute the load of the data analysis. I'm going to say all of them. This takes a while. Now we have our heritability measurement files ready. Though if you had a maximum of 60,000 traits as is recommended, we're likely to have multiple files. To create a viewable, complete structural nifty image file, we must merge the files. Firstly, you must have the FSL software installed. As you can see, we have our KA Voxelwise files produced here. Now we're going to merge the necessary files together to produce our nifty image file. We're going to run this to be able to run our FSL software, and then we're going to run the following command. And then we will run the next command. And now we're left with one file, kah2nii.dc, and this is our nifty image file that we should be able to see in Mango. For example, if we open up the file in Mango, we are able to go through and see images of the brain.